Okay, okay, all right. So I'll get started. Let's see. So let me first start with the review of the first 2 days, right? So, okay, we discussed so far that phase diagrams are important. Like we have the phase diagram for fluids, for magnets, like QCD, basically for anything we can write down a phase diagram. Okay, and we've stressed that we need to understand the analytic structure of the partition function Z to understand the phase transitions, because we emphasize that the phase boundaries are actually not analytics in the partition function Z, which can be written like this in statistical mechanics, right? So here Z is the partition function, beta is the inverse temperature, K, here the K's are like set of phenomenological constants or coupling constants in the QFT language. This L is just a function. It has a symmetries of the Hamiltonian. We write that down. Usually we go with lambda potential. And this denotes a path integral over this phi, which denote all possible degrees of freedom in the lambda function. Okay. So this mathematical object is extremely close to what we write down in the high energy physics, right? So here, this time, this Z is called vacuum generating function. This W is called, it's the generator of the connected diagrams, connected Feynman diagrams. And this S is the action. So this is like the Euclidean path integral in Euclidean QFTs, but the story is the same with the Lorentzian. You just do a big rotation and you get like an I here. Apart from that, it's basically the same. And okay, so that means understanding of such objects is, understanding of such objects is useful in both statistical mechanics and high energy theory, in field theory context. Good. So as we said, like the analysis of these partition functions gives us phase diagrams, but if there's an analysis where all first derivatives are continuous, such that any such first derivative is continuous, then we call such analyses continuous phase transitions, right? So if any of the first derivative was discontinuous, we would call it first order phase transition. And if all of them are continuous, then we call it continuous phase transition. And we reviewed that in the so-called lambda formalism, we can see that the continuous phase transitions are associated with the critical phenomena. Okay, and it explains qualitatively and predicts the spontaneous symmetry breaking in field theories, the massless excitations, which are also called Nambu-Goldstone bosons, which in turn predicts that there needs to be long-range interaction, which yields ordered phases. Okay, so this is like the relations. Like if you have an ordered phase, you can expect a long-range interaction, which in turn means there should be massless excitations. Okay, and the lambda formalism also predicts that there needs to be scale invariance at the critical point, which actually explains why we have these critical opalescence. As you may remember, we observed that at the critical point, the fluids become opaque. Actually, I already shared a video of it in the Slack channel. You can see it with the experiment done. You can literally observe that in an everyday experiment. And the reason that it becomes opaque is because all kinds of fluctuations, like all fluctuations of all frequencies become relevant at that point because the theory is scale invariant. It doesn't have an intrinsic scale. Well, roughly. Okay. So, okay, we also classified the interactions. We said a general interaction is of this form, where this object is like the two-point function, Green's function, propagator, whatever you want to call it. It has some Pavlov behavior, and it has some exponential behavior. And in this exponential behavior, there is this parameter psi, which is called correlation length. And it can be either finite or infinite. And this is indeed what differentiates a shorter interaction from long-range interaction. A short-range interaction means this psi is finite. And in QFT terms, it's basically indicating there's a massive particle, like quantum flavor dynamics, the weak interactions, because we have massive W boson and Z boson. On the contrary, if psi is infinite, that means the interaction is long-ranged, and we have in QFT terms, massless particle, such as QED, where quantum aerodynamics, where photon is massless. So it's a long-range interaction. And at the critical point, psi is infinite. So indeed, we get these long-range interactions. That's so far so good. Are there any questions so far? Just reviewing what we talked about past 2 days. Good. Now, yesterday we mentioned that we need a cutoff in path integrals. So what do I mean by a cutoff? Again, I am assuming you don't know path integrals, like you don't have to. In these notes, it would be great if you knew, but I'm assuming you didn't take QFT course or anything, so you don't know path integrals. Just think of this as an ordinary integral. What this notation, this thing basically means that I am not integrating everything. Like if this was an ordinary integral, let's say just dx fx, and this is a to infinity. What this means is that basically I am integrating for values of x above a, right? In the ordinary integrals. This is very similar to that. In this case, I am integrating over functions, all possible functions, because this is a functional integral, but I am restricting only to those functions which does not fluctuate at very high frequencies. In other words, the details below a scale are blurred. Like I do not probe very microscopic details. They are blurred if the distance is less than this lambda to -1. Okay, this is what it means. In other words, we do not have degrees of freedom that probe these distances. And I need to do that because after all, as we discussed, I'm using continuous fields to describe something basically which is discrete, right? Because if you consider, let's say, a magnet, it's a lattice side. I have discrete spins, discrete objects, but I am approximating it, I'm modeling it with a continuous field. So that means I shouldn't really probe too much. If I probe too much, then this continuous approach will break down. So instead, in statistical mechanics, that just makes sense because there is a lattice spacing, it's actually lattice, so I need to have this UV cutoff. In the QFT, you can argue that, okay, I have these fields, they are fundamentally fields. Like I'm not approximating anything discrete with a continuous thing. Okay, they are continuous fields. But in QFT, there are 2 cases. The first case, it can be so-called non-renormalizable model, which means I really need to have this cutoff. Okay, I cannot consistently get rid of it. So that means I have a UV cutoff, which basically says that theory is only valid up to some energies. As a standard example of this, we already talked about Fermi's 4-fermion interaction, for 4-fermion theory for weak interactions. Like this was at the times where we didn't know about W boson and Z boson. So he wrote down a theory to explain weak interactions. It was successful, it was working, but it was not renormalizable, meaning that you couldn't use that theory for any energy. And for that theory, the path integral had to be limited to the UV cutoff, which is around 300 GeV. Now, in the other case, you may have a renormalizable QFT, which means I can consistently take lambda to infinity. Well, actually, there would be some infinities, but I can get rid of them in renormalizable theories. This is why I'm calling it renormalizable. Actually, this is a bad terminology because we're not normalizing anything. But it basically means that we can get away with taking lambda to infinity, even though there are some divergences, etc. I can deal with it. It's consistent. Now, in such cases, I don't need it. Okay, fine. But that doesn't mean the theory is right at all energies. What it means is that if a theory is renormalizable, that means I can take this to infinity, fine, and it will give some predictions at any energies. However, those predictions may or may not match the experiments. So they may be true at low energies, but after some point, they may diverge from the actual experimental values. Because for instance, maybe the theory is missing some particles. Let's say there's a heavy particle, and I write down a renormalizable theory, which doesn't have the heavy particle. It will give me consistent results, fine, but it will not predict correctly if I'm at very high energies because I didn't take into account that heavy particle. Okay, so in the case of renormalizable QFTs, I don't have to have a UV cutoff, but it's advisable to keep one because to remind ourselves that, yeah, it may not necessarily be true at all energies. Okay, good. Now, we discussed that we can change this cutoff, right? So I can say, okay, I already gave the example earlier. So let's say I have this path integral, d phi, something blah, blah, blah. And I am considering functions which fluctuate with, let's say, lambda inverse is like 1 micrometer. So I am ignoring all the details below 1 micrometers. Or I can write down like d phi, blah, blah, same thing, lambda inverse, around 1 millimeter, right? So both of these are fine options. And especially if I'm trying to explain phenomena at like microscopic scale, let's say at 1 meter or whatever. So both of these are short ranges for the particular case. But there should be a difference between these two, right? And that difference is actually change of coupling constants. So we argued that let me get rid of, okay, quickly, let me get rid of that. Okay, so we argued that the difference is basically the change of coupling constants. So coupling constants in the Lagrangian or phenomenological constants, they're the same thing, are regulator dependent. Now in a statistical mechanic problem, these are usually like things like temperature, pressure, compressibility, rigidity, viscosity coefficient. For example, viscosity coefficient, it's a difference between, if you don't know viscosity, it's the difference between like a honey and water. Like both of them are liquids, but they behave differently, right? Because they have different viscosity. This coefficient, for example, is lambda dependent, and so on. And in QFT, in high energy physics, these are usually like mass or like interaction coefficients. For example, the mass of a particle is lambda dependent. When we say, let's say, mass of an electron, it's actually not constant. It depends at which energy scale you are doing the experiment. Okay, like mass of particles or interaction coefficients, they are all lambda dependent. So this was the origin of the RG. Like this is the backbone of the RG formalism. You need to realize that everything is kind of scale dependent, the scale at which you do the experiments. Good. Now, if as we get rid of the details, further and further macroscopic details, we are set that we are flowing to the IR behavior of a theory. Okay, let me start with any QFD or any model, statistical model, doesn't matter. And let me do the RG formalism. Let me just flow. I'm just getting rid of more and more details in the macroscopic details. Then we are set to flow to the IR behavior of a QFD, which is usually a CFD. Okay, it doesn't have to be, but which is usually a CFD. Okay, good. And are there any questions so far, by the way? Please interrupt me if you have any questions.
I got a question regarding to the very beginning. Yesterday and today, you have mentioned that we actually have a lattice, which is a discrete structure, as you would appreciate it. But since we cannot calculate it, we are appreciating. We are calculating it as it's continuous. And is there any way to calculate the approximation error?
It's a good question. Firstly, I don't know. Maybe there is one. But here's the thing, like we shouldn't be doing this all the time, right? So I am approximating a lattice with a continuous field because I will be interested in the phenomena which happen around a fixed point. So actually that's what I'm trying to motivate. Like around fixed points, it really will not matter which theory you are considering. They will give you exact, like there won't be any error. Like at critical phenomena, like as I said, let's say these critical exponents, I talked about them yesterday. Whether you calculate them with a lattice theory or whether you calculate them with a continuous field theory will not matter. You will get exactly the same results because there's this thing called universality. It doesn't matter which theory you use as long as they flow to the same CFD in the universality class. Like, so 3D, let me write it here. So 3D Ising model, there's a lattice model, or 3D scalar boson, Euclidean QFD. So both of these flow to the same 3D Ising CFD. So I want to compute some stuff in this theory, right? But instead I am using this theory, which flows to the same CFD. And it gives me exactly the same answer. So there is no error here at the critical point. However, if you are not doing critical phenomena, like if you're interested in some arbitrary position in the phase diagram, let's say, we have this phase diagram for fluids, right? It goes like that, like this. Here's solids, liquid, gas. Let's say I'm interested at behavior at this point or something like that, at some particular energy scale. We don't know how to do it. And if you approximate with a continuous field, there will probably be an error. Okay.
Okay,
But,
since because it's just one point and we are analyzing the non-analysis, so it won't basically, there won't be basically a difference.
in difference what? So, sorry, I couldn't answer.
Because we are checking the non-analysis points, I think that there won't be a difference because we are checking only one point actually, which is the critical point.
Well, yeah, but critical point is the important point. Like, so it's not just an arbitrary point in the phase diagram, but like it is related to many behavior in general. Because as we discussed in the IR, in the randomization group flow, just start with any, actually, did I draw it? I think I drew it here. Okay, so this is the phase diagram for magnets, right? If this left diagram, this is the phase diagram for magnets. Like we have a phase transition here, this line, we have a critical point here, this point. Now start at any point, okay, any point. And as you do an RG transformation, it will flow to one of these critical points. There are like 5 of them here, 1, 2, 3, 4, 5. So that means even though if you are not at the critical point, as you go to IR, you will move towards a critical point. So understanding critical points not only explain the critical data, but also any point, any QFD as you move to IR or their microscopic details. Okay, so if you're interested in a microscopic behavior, then understanding fixed point is important. If you are interested in understanding microscopic details, like not macroscopic phenomena, then yeah, there's a difference.
Okay, I think I get the general point. It will be more clear when I do the calculations then. Thank you.
Okay, no problem. Good. So we mentioned this. Yeah, so, okay. All right, so we were here, yeah. So we say, okay, the general theory usually float SCFT. Good. Okay, actually we were right here. Nice. So RG flows of coupling constants are usually shown on phase diagrams, as I was just saying. So this is like the phase diagram for uniaxial magnets, right? This line is the critical line. If I move like this, I have a first order phase transition. Here's the blue point is the critical point. At that point, there's a second order, there's a continuous phase transition, etc. And this green line is the disordered phase. So if the external magnetic field is 0, and if your temperature is high enough, then the magnet is disordered. So it doesn't magnetize. It's just like ordinary matter. However, if you are at a low temperature, at 0H, it is magnetic. It magnetizes even at 0H field. Okay, so this is why this region is disordered phase and this is ordered phase. Good. Now, if we analyze the RG flow for this diagram, for instance, now any point here, like any point here, within IR, move to this fixed point at t is equal to infinity. So if let's say consider a particular, let's say nickel magnet. I don't know its Curie temperature. Let it be, I don't know, I'm just making it up. 1000 Kelvin. Okay, let's assume it's a 1000 Kelvin. Now, this IR flow tells us that if I consider a nickel magnet with T is equal to, let's say, 2000 Kelvin, as I move to IR, its behavior will be not different than nickel magnet at infinite temperature. Okay, so if I consider T is equal to 2000 or 3000 or 5000, doesn't matter. They will all flow to, like there are these points, all flow to this fixed point. So their behavior is explained by infinite temperature, which is this disordered phase. It makes sense. Like if temperature is infinite, that means thermal fluctuations dominate any kind of ordering. It's random. And at T is equal to 2000, this is what we observe as well. There is no magnetization, it's random. So it's not different than T is equal to infinite. Okay. Likewise, if you are at this point, for instance, or this point, like these points, they will flow to this ordered sink. So their behavior at IR will not different than having an infinite external magnetic field. So they will be ordered. Like if you have a magnetic field which is infinite strength, then all of the spins will align with it. Because if they don't align with it, that would cause infinite amount of work, right? If you have an infinite external magnetic field. So all of the spins should point in that direction. There should be magnetization. And indeed, this is what we observe at these points. So these points flow to this fixed point. So fixed points explain the phases, they explain the bulk phases of matter or substance or field, whatever you have. Good. So this we discussed yesterday as well. Now, so we need to understand fixed points. Okay, sure. But we don't know how to do it in general because we have no way to solve strongly coupled field theories. Okay, so we don't know how to do it. I listed some approximations yesterday. Like one of them was to start around the Gaussian fixed point, which is the free theory, like it's this guy. Okay, and look for new ones. Like just start around there, do some computations, try to find if there's another fixed point around. And indeed, in QFT, with the scalar Lagrangian like this, Wilson and Fisher did this. They found a new fixed point if d is less than 4. This is called Wilson-Fisher fixed point. And this is the fixed point which explains Ising universality class. So for instance, if you understand this fixed point, then anything you compute would exactly match a lattice theory's computations, their predictions as well. So there won't be an error because of universality. Okay. So this is true only for these less than 4. If d is greater than 4, then the Gaussian fixed point explains Ising universality class. Okay, so it's basically free. Good. And and we said that we can okay, we found this fixed point, but we don't know how to compute stuff here. So what we do is, because this is strongly coupled, what we do is take the dimension d 4 minus epsilon, because if this is d is 4, this is basically just next to this one, Gaussian fixed point, which we know how to solve. So take d to be 4 minus epsilon with epsilon very small, take that, do the computations, and at the very end, take epsilon to 1, okay? So this is called epsilon expansion. Of course, we won't be doing this. It's like, this is not what I'm doing, this is not what I'm promoting anyway. I'm saying we shouldn't be, we can do this, but I think there's an alternative approach, and maybe better, I don't want to self-promote, but which is to use CFDs instead of doing that. Okay, there's a similar technique, Larsen expansion. Please see my notes. Okay, before I finish the review of the first 2 days, the final reminder, we said that there were various quantities that diverge near a critical point, right? So these are experimentally computable stuff, like the heat capacity or compressibility of a fluid, or the correlation, this is not experimental, I guess, measurable, but it can be deduced. So things like this, we can do experiment to plot them, and they really all behave as simple power laws with these exponents called alpha, gamma, nu, and so on. There's also beta, delta, etc. They are universal in the sense that, for example, alpha is 0.11 for any theory in the Ising universality class in 3D, or nu is 0.63. And one of the aims of the CFT is to understand this. So we will use conformal field theory to derive this. So we will derive them using CFTs. Right now, they are experimental inputs. Okay. Also, they can be computed by Monte Carlo simulations or lattice computation, stuff like that. Good. Any questions? Okay, great. So let's see. Okay, so we talked about RG. Where were we? Here. Okay, good. We've done this. Yeah, but there's this table, for example, where I classify fixed points by the value of the correlation length, whether it's 0 or infinite, and what do they correspond whether they correspond to bulk phase, triple point, stuff like that, and with some explanations. You may want to look at this if you're interested. Table 2. Okay. Now, good. So we have these critical exponents, and we want to somehow compute them. To understand them, I'll first do something basic. It will be a review as well. I'm sure many of you already heard about dimensional counting, but I will do it nevertheless. Actually, maybe you haven't heard. Yeah, it's in QFT. Like it depends on whether you're taking QFT course or not. Okay, so we consider a general Lagrangian. I'll be like using like the high energy theory terminology, but it will be valid for like condensed matter, statistical mechanics, etc. Okay. Let's consider Lagrangian. I have this coupling constants K and some operators phi. Again, this phi can be like a scalar operator, vector operator, so on. For simplicity, I'm taking them to be like scalar, but they don't have to be scalars, okay? They can be anything. And a general Lagrangian can be written of this form. There's a bunch of terms with some operators, x-dependent, and with some coefficients, x-independent, okay? So, and this is the like the action. So this is the action, and there is like a limit. This is a UV cutoff to the integration. Okay. Good. Now here's the thing. I have this thing. I scale x by a parameter L, a positive real number. Now if I do this, then this action becomes like, just a second. I get an update at this very moment. Sorry. If I do this scaling, then this action becomes like this, right? So x becomes L minus 1 to x, here, and this cutoff, it was basically like the integration limit. It changes as well. It's the integration limit. Now, if I also change the integration limit, right? If I also change lambda goes to L times lambda, then this will be same again, right? It will be like, this will be again lambda d to d L minus 1 to x, ki L lambda, or L lambda L minus 1 x, right? So and this will give me, if I equate this thing and this thing, it gives me this equation. Okay, so it actually shows us a relation between coupling constants and operators at different length scales. Now, this is in general a complicated thing. Like ki, the behavior of the coupling constant ki as lambda is different. It's a complicated, it's just a flow. Like this, let's say there's a fixed point here, it flows like that, like that. It may be doing something complicated. We don't know in general. However, around the critical point, it either flows there or goes away from there. Like it's like this, right? It is the only singularity for the flow. So we can linearize the behavior of ki around around the fixed point, not necessarily a critical point, around the fixed point. So around it at leading order, we can assume it is it's of homogeneous form, right? So we can do that. Now, this ki is called the mass dimension. Like this is the notation. If I write this thing, it will denote, at least for this section, the mass dimension of x. The reason I am saying mass dimension instead of like the scale dimension or length dimension or whatever is because that's the convention used in high energy physics. Okay, so that means this ki L times lambda is equal to around a fixed point L times the mass dimension of k times ki lambda. Now, if I put this back here, then I get this equation. Okay. Now, and also, by the way, when I say something is homogeneous form, let me actually show it. So, okay, yeah. If a function satisfies this thing, I'm calling that it's homogeneous in the variable xn. Okay. This is what I mean by homogeneity. Good. Now, and this clearly shows that the coupling constant is homogeneous function. And this is the mass dimension, and I'm inserting this back to here, which gives me this relation for operators. And one word, I keep saying operator for this O's, because when I quantize the theory, like there will be operators that I can hit on the vacuum to generate some states, right? If it's a free theory, or if it's around free theory, I can hit the operator OX on vacuum to generate something like one particle state almost. It's not really true, but almost something like this. I actually need to smear this if it is a Lorentzian signature. I don't need to, if you need some details, but it doesn't matter. So I'm calling these as operators because they are really operators. You can use them to generate states in Hilbert space. If you don't know about Hilbert space or this discussion, it's fine. Just take my word, but just assume that this is the terminology. Okay. So these operators always transform like this. And here, if instead of using them lambda and lambda x, okay, sorry, how should do I say it somewhere? Oh yeah, right. So instead of labeling O with lambda and x, if I label them with lambda and lambda x, then it becomes like this, right? Lambda x doesn't change under this transformation. And like this transformation, this plus this, and lambda was changed to L lambda. So, okay, it was not clear, I guess. So I have this, I inserted this here to obtain this equation, okay, this star equation. Then in star equation, I say, okay, instead of labeling O with lambda and x, let me label O with lambda and lambda x. And when I do that, this O becomes homogeneous in its first argument. Okay, we get 1.25. And for homogeneous functions, we define this mass dimension of O like this. So this equation tells me that if you sum mass dimension of the O and mass dimension of a coupling constant, it sums to D. Okay. So mass dimensions of coupling constant and operators sum to D. Good. Around a fixed point, it's leading order. Like you cannot do this everywhere because they don't need to behave homogeneously in the first place. Like I've seen this like in many books like this. I guess they were being very quick. Like you cannot define this mass dimension everywhere. You need it to be homogeneous. You need it to scale like homogeneously under scaling of the energy, which only happens around the fixed point because you can linearize the action. Linearize the action of RG flow. Okay. Yeah, good. So this is the equation we get. Nice. Now, here is the thing. Consider this equation again, right? So if I have, let's say K, let's take K to be like the mass. Let me actually write it. So I have M squared, like literally the mass. So M, let me write here. M squared, the mass squared, L times lambda is equal to L2. Well, mass dimension of mass is just 1, so mass squared is just 2. L squared times M squared lambda, right? So that shows that if I go from lambda to L times lambda, mass square will go to mass L squared times mass square, right? So if I change the energy scale like this, accompanied with x goes to L minus 1 to x, then mass will increase. Mass will increase. So if the phase diagram was something like this, actually I should be, let's see. Maybe I should try it like this. Okay, that will be easier. Okay, so let's see, M squared lambda. This is the Gaussian fixed point. Okay, so let's say I start with a small M squared. I'm around the Gaussian fixed point. Let's say I start with this point, that. We saw that M squared goes to L squared times M squared under RG flow. So it should go here, right? It flows to this point, and it keeps flowing like this. If it was non-zero, it will become even more non-zero. So if you were just a little bit above the fixed point, it will take you away from the fixed point. Okay, let me repeat what I'm saying. If you were, let's say, just a little bit above the fixed point, this red dot, then as you do RG, M squared will keep increasing, so you will move away from the fixed point. So that is, well, important. But think of something else. Let's say this lambda. Let's assume that lambda changes like L2 minus cube lambda. I'm just making it up. Okay. So if initially, if lambda was non-zero here, let's say lambda was initially something non-zero, then as I do RG, it will get smaller. So it will flow to the fixed point. So if we are at a fixed point, if you nudge it, if you perturb it a little bit, if you get a non-zero lambda, the RG flow will bring it back to the fixed point. Does it make sense? What I'm saying is, is it making sense? Okay. So then we call this lambda an irrelevant direction. Because even if I am not at fixed point in this direction, the RG will bring me back to the fixed point. On the contrary, M square is a relevant direction. Even if I am just a little bit away from the fixed point, the RG will move me away from the fixed point. Okay, so that means I need to tune M square to reach the fixed point, but I don't need to tune lambda. Okay, so that means need to tune M square because it's a relevant direction. That means if it is not exactly at the fixed point, it will go away. But I do not need to tune lambda. It's irrelevant because even if it is not exactly at the fixed point, it doesn't matter. It will flow to it by itself. So think about fluids again, right? And so it's like this.
Can I ask something really quickly?
Yes, please.
Like, what do you exactly mean by tuning? Are you considering just...
I'm about to say this. Just
like
let me
couplings?
say this example, then ask me again. Okay, if it's not clear.
Okay.
Okay, let me say
is it related to, bare couplings, unrenormalized?
No. There's nothing to do with quantum field theory. You can just think of this as classical mechanics as well.
Okay, I'll wait.
RD had nothing to do with QFT. But you use it in QFT, and it's very useful. Okay, let me give this example, it will be clear. So let's consider the phase diagram for fluids, like water, for example. So here it is solid, liquid, and oops, there's nothing here. And yes, right? And here this is like the pressure. This is the pressure. And this is the temperature. Now here's the thing. If I want to observe the critical operations, for example, the critical behavior, I need to be exactly at this critical point, right? So I need to tune my pressure and tune my temperature so that I am exactly at this point. If my temperature is a little bit different, I don't observe it. If my pressure is a little bit different, I don't observe it. That is because pressure and temperature are actually relevant coupling constants. Under RG, if they are not exactly at the fixed point, they move us away from the fixed point. So I need to tune them manually. But for example, I only need to tune two parameters. Like I don't need to tune a third molar density or like some, I don't know, electric field or anything. Like for example, electric field here, if it is different, it won't affect things. Like you get my point, right? So 2.2 parameters here are relevant parameters, pressure and temperature. I need to tune them to reach the critical point, but I don't need to tune anything else. So I was talking about the dimensionality of the phase diagrams at the very first talk. This is actually why it's important. Like the dimensionality of the phase diagrams, actually the dimensionality of the fixed points determine how many things you need to tune to reach a critical point. For uniaxial magnets, for example, this was a phase diagram. Here is like a first to first transition. Here's the Q temperature. This is again temperature, and this is external magnetic field. Now, to be at the critical point, to be at exactly here, I have to make sure that T is equal to Curie temperature and external magnetic field is equal to 0. So I need to tune two parameters again. And this is no coincidence because uniaxial magnets and fluids are in the same universality class. Like if I needed to tune 3 parameters, then the same CFT couldn't be able to explain this. Like, so for easing universality class, you should have 2 parameters to tune. Like if you come up with something experimental, let's say, oh, I need to tune 4 parameters to reach that, that cannot possibly be explained by the easing CFT. Okay, So this is the reason why the same CFT explains. I'm trying to.
Is it also important what the dimension of the, if you have a critical point or a critical line or a critical surface, does that enter into the picture? How many operators, not operators, but what you have to tune?
It does, yeah.
Okay.
It does. Yeah, I'm not doing anything complicated here. I'm just using universal crystals is the simplest CFT possible. But it's like, if you ask me, it's the most relevant one because it explains like water, like many things like we only have explained by easing. So it's good enough. Even though it's simplest, it's very useful. And it's like the starting point for many discussion. But you are right. If you were to consider more complicated, like in the case of helium-4, for example, where there's actually a critical line, it's in the Heisenberg universality class, not Ising universality class. Things are different. But yeah, it's the same storyline. Yeah, the arguments we are making here, they're well there as well. It's just it will be a bit different. Okay.
I also have some questions about universality classes, but maybe we can discuss it in the discussion hour.
Sure.
Because it will take too long, maybe. Okay.
I'll be around in discussion now. Okay. Since we have limited time, this is why I'm trying moving fast.
Yeah, I totally understand.
You can ask me, please interrupt me if it is relevant what I'm talking about right now. But if it is general, we can discuss later. Good. So what we learned that, okay, I had to tune m squared here, like in this example, it was the relevant direction, but I didn't need to tune lambda. Now, if we get back to our notes, like what we're talking about, so we saw that, this is the equation, we saw that K is actually relevant, Ki is relevant if the mass dimension of it is bigger than 0, because then it will get larger and larger under RG transformation. And it is irrelevant if its mass dimension is less than 0, because it will get back, like it will go back to the fixed point, even if you perturb it a little bit, even if you make it non-zero. Okay, but we have this equation. That means I can classify the operators in the Lagrangian into 3 classes. If the mass dimension of the operator is less than d, okay, let me actually use this. If it is less than d, then it's called a relevant operator, because that operator is associated with a direction which we need to tune. If it's greater than d, that is an irrelevant operator. Its contribution will diminish as we go to IR. If it's exactly d, that's marginal. Its contribution doesn't become more and more important at IR, or less and less important at IR. It becomes like constant. Okay, so we have to consider them, but not really that important. Good. And most of the time, if you are doing, let's say, an epsilon expansion, if you compute next order correction terms, a marginal operator becomes either relevant or irrelevant. So as you do like higher and higher order computations, marginal most of the time don't remain marginal. They become either relevant or irrelevant. Okay. Are there any questions so far?
For irrelevant operators, like looking at 1.25, since the exponent of L is negative, yes?
Yeah.
Like you can actually set it to 0 for some L, That's what you mean, right?
Could you repeat what you said?
Like, since the exponent of L is negative.
For which case?
1.25.
Yeah, for this
for
equation.
irrelevant operators, yes.
Yeah, for irrelevant, yeah, exactly. For irrelevant operators, no, I'm not setting them to 0. For irrelevant operator, it basically means.
But it goes to 0.
Sorry?
It goes to 0, so.
Yeah, it goes to 0 by itself under RG. Exactly. Like if I have this irrelevant, let's say I have a Lagrangian, right? I have something, let's say delta phi square plus some phi square plus some operator O. Okay. So this operator itself goes to 0 under RG if it is irrelevant. So it drops out of the Lagrangian.
Yes.
And here is one nice thing. Like I want to talk about this. If you guys remember, yeah, right here. So if you guys remember, we were discussing this lambda formalism, right? This all this stuff, this good stuff. And to explain it, where is it? Where is it? Yeah, anyway, I guess I am sure I wrote it somewhere here. Okay, just give me a second. Oh, there we go. Right. So when I first introduced Landau formalism, right, I said, okay, we need to consider a general function Lki and M. It should have this symmetries of the Hamiltonian, right? And I said, okay, technically we can include M to 6, M to 8, right? Let's say M to 2000, sorry, 200, whatever. So, but I said, we are truncating them right here. We are truncating them. It's not warranted in general, but it will be valid as long as it's applicable. And this is why is the case. These operators are irrelevant if the Landau formalism is applicable. So even if I included them, they will just go to 0 under Argy transformation, okay? Which is why I could just truncate it and still get the correct result, okay? So by the way, and the renormalizability of the quantum filters is also related to that, like not related to that, but you can also understand them a little bit better by using Argy. Yeah, like Fermi's, like for example, Fermi's theory, you know, I keep saying it, my renormalizable theory of explaining big interaction. So that theory, well, was not valid at high energies because it was non-renormalizable, that term. It goes to 0 as you move to IR, but it blows up as you go to UV. So since it blows up as you go to, like for them, this term, I'm dropping them. They are non-renormalizable, meaning that I don't need them at the IR, at macroscopic things, because they will just go to 0 by themselves. But as I go to high energies, if I go to UV, then these actually will blow up. These terms will blow up. So they will kind of kill the model and make it not usable at high energies, which was the case, which is the general case with non-renormalizable theories. There are some terms in Lagrangian that they just blow up. Okay, so roughly. So this is the idea. Any questions so far? Okay, good. So I have like a little bit more time. Where am I? Just give me a second. Yeah, good. So this is how we classify operators. Nice. Now, so the operators can be anything in general. Like for example, I gave some examples. Like it can be like a 5 square, 5 to the 4, 5 to the 6, blah, blah. Like it can be the stress tensor T mu nu, which is like this operator in the case of the scalar Lagrangian I wrote down earlier. It can be like a vector field. It can be higher spin currents, whatever. When I say operator, it can be basically anything. And in fact, unless we are near a free theory, we don't have a way to write them schematically anyway. Like I can write down an operator like this, for example, phi, delta mu, delta nu, delta rho, phi. Let's say this is O mu nu rho. This is like a like think of it as like a spin tree operator. Okay, spin tree operator. This thing, this schematic form, it's actually not really valid unless you are doing free theory or around the free theory, which is what we most of the time do because we don't know anything else. But yeah, in strongly coupled theories, this would become something not really expressible. It would just be like, oh, mu nu rho. I wouldn't be able to write it down in terms of these phis like that, which I will come to in a minute because in the 3D Isaac model, this is exactly what happens. I will show it. Good. So nice. Let's see. So if I consider these operators, as I said, like these 5 operators, now, what is the mass dimension of phi? Well, the standard way to do it is that I have this Lagrangian, right? In general, it could have the coupling constant, let's say C1, delta y square, C2, maybe I should use case. I used K earlier. K1, K2, let's say phi, K3, phi square, K4, T mu nu, blah, blah. Like a bunch of operators in Lagrangian with some coupling coefficients. Now, as convention, we normalize phi such that, the coefficient of the kinetic term is just 1 or 1/2. Okay, so this is how we normalize it. This is actually what we did. Anyway, this is how we normalize it. So we can write down L Let's just delete this. Okay, so we can write down L like 1/2 delta phi square plus now some coupling constants, K3 phi square, blah, blah, blah. Now, if I normalize phi like this, then I can immediately compute the mass dimension of phi because the mass dimension of Lagrangian needs to be D. Why? Because I have e to the I, well, actually, I don't need to use action to, okay. Why? Because I am action, let me just write this way. Action is integration of Lagrangian, right? And action needs to be, it needs to be invariant under the scaling. It doesn't depend on X. So it shouldn't have any mass dimension. The mass dimension of action needs to be 0. It doesn't depend on X. I integrated X. And that means the mass dimension of this combination needs to be 0. The mass dimension of ddx is minus D. Hence, the mass dimension of Lagrangian needs to be D. Okay. Now, was this clear? Okay. Now, as the mass dimension of Lagrangian is D, and as the mass dimension is something additive, something like true term by term, that means the mass dimension of Lagrangian needs to be D. So the mass dimension of D needs to be, this term needs to be D. The mass dimension of this term needs to be D. This term needs to be D, etc. Okay, individually. Because I'm summing them, they need to have the same mass dimension. But the partial derivative has mass dimension 1. You can think of it this way. Length has inverse mass, like x has a mass dimension -1, right? Dx has a mass dimension -1. D over dx has the mass dimension 1. Okay. So that means if I have, let me just write here. If I have, oops. If I have d phi square d, that means the mass dimension of d phi is d over 2. The mass dimension of, actually this is like this is delta phi. Delta. The mass dimension of delta plus the mass dimension of phi is d over 2. This is just 1. And this fixes the mass dimension of phi as d minus 1 of d minus 2 over 2. Okay. So this is the mass dimension of a scalar. Now this is the mass dimension of a free scalar, right? Which is what we get here. So that means the O1 has a mass dimension d minus 2 over 2. This operator has d minus 2. It's like phi square. This is phi to the 4, so twice the mass dimension, and so on. We can compute these or these. And T muni always has the mass dimension d. It's always marginal. Okay. So I can compute this, no problem. And here's a nice part. I said that you need to tune 2 parameters. Like if you are considering fluids, you need to tune pressure and temperature to go to critical point. For uniaxial magnets, you need to tune external magnetic field and temperature to go to critical point. That means the CFD that explains them need to have 2 relevant operators. And these relevant operators are denoted as sigma and epsilon. And if you know their mass dimension, you can compute all of these critical exponents that we talked about earlier. If you remember them, like we were talking about here, like we were saying, oh, there are like a bunch of critical exponents that we want to compute, like alpha, gamma, nu, like all of them. You can compute all of them by just using the mass dimensions of these 2 relevant operators. So if we can compute the CFD data, like the knowledge of these operators in the CFD, then we can get the critical phenomena, just like that, no problem. Okay, is this clear so far? Good. Now, but here is one thing though. You may actually, does anyone see any contradiction here, what I'm talking about? Like, maybe it would be easier for you to see the contradiction. Like, these are the experimental values for alpha, gamma, nu, etc. Right? Actually, they're like more terms here. Let's see. I just wrote like first few digits. And these are the relations I'm providing you with. Now, here is the tension. Maybe you haven't seen that, but these mass dimensions that we compute like this are always fractional things, right? It's like d minus 2 over 2, 2d, d minus 2, like they're like 1, 1/2, 3/2, things like that. But these exponents, alpha, beta, blah, 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 they are really rational, real numbers, not just some fractions 4 over 3 or 11 over 3 or whatever. So it doesn't make sense that we can use this to explain that. The reason, like the resolution is that it's true that this formula that we use is only valid if we are using the free, like we use the free scalar, right? And free scalar is the Gaussian fixed point. So if the Gaussian fixed point is explained as 3D CFT, then yes, this formula is correct. But the Gaussian fixed point only explains CFTs if dimension is 4 or larger, if you remember. So these equations are valid only if we are considering like a 4 or higher dimensional critical phenomena. But these values were for 3D CFT. Now, don't worry, we will have this, these will exactly be true at 3D as well, with the small change that instead of writing like this epsilon or sigma, we will have delta epsilon, delta sigma, so-called scaling dimensions. So the actually correct formulas will use not the mass dimensions, but the scaling dimension. And there's a difference between these two, which I will talk about in the next 15 minutes. Then it will be good. Okay, so yeah, this formula is correct, but instead of using this mass dimension, we will use scaling dimension. Good, because as you all know, it's not the Gaussian fixed point, but it's the Wilson-Fisher fixed point that explains the critical phenomena at 3D. Okay, this was for Gaussian fixed point because we use the values for free theory. Like these are free theory. But here's the question though. Oh, before that, let me show this. And also, this is also interesting. And it's very interesting. The thing is, did I write them down? Yeah, maybe I didn't, but okay. So yeah, in the Gaussian fixed point, I have these two operators, two relevant operators, phi square and phi x square. So, sorry, phi x and phi x square. Okay, I have two relevant operators. Let's call them O1 and this is O2. Now, as you can see, the mass dimension of O2 is simply 2 times O1, right? It has to be like this. If this is phi x and this is phi x square. But here's the problem. If the sigma and epsilon, what I've been calling sigma epsilon, are just phi and phi x square, then these mass dimensions are actually just like this thing is just twice this thing, which is true at free theory and with interaction. But when we go from Gaussian fixed point to Wilson-Fisher fixed point, this phi x becomes sigma x, and this phi x square becomes epsilon x. And I denote them like this. And I can no longer denote epsilon x like phi x square. You know, I was talking earlier about how we cannot write things like standard schematic form. It simply doesn't work. Because this scale dimension of this guy is no longer twice this guy. Like its mass dimension gets these anomalous factors. We denote them by gamma. Okay. And in fact, I think I wrote down the numeric values. Did I write down numeric values? Yeah, right here. So for instance, d minus 2 over 2 is just 1/2, right? At d is equal to 3. So delta sigma is 0.508, and delta epsilon is like 1.913, right? I'm adding, no, sorry. It's just this one, my bad. It's 413. Okay, so think of it this way. Earlier I had phi, it had the scale dimension d minus 2 over 2, 1/2, and I had phi square. It has a scale dimension d minus 2. This is 2. which is 1. Then under RG flow, this was at the free point. It was weakly coupled. Then I flew to a strongly coupled theory, and they become, delta phi become from 1/2 to 0.508. And the phi square become, now I denote them as epsilon instead, and this sigma instead, because they are not no longer square of each other. I shouldn't be doing denoted that like that. It has a scalar dimension like this. It's a lot more than twice the original one. And actually, this is the indication that the theory is strongly coupled. Like, if you look at like this, if I were to do like a perturbation expansion, I would take this to be 1. If you're doing perturbation expansion, the mass dimensions are just d minus 2 over 2 for any scalar. It's called engineering scalar dimension, right? You expand around free theory because this is what you know to do. We don't know how to compare other path integrals. But experimentally, we see that the scalar dimension is far from 1. It's like 1.4. It has a huge anomalous dimension, indicating that it's strongly coupled. So the traditional methods really don't work here. That's another way to look at this. Is this clear? This argument, this discussion? Okay. Now, okay. So we said good. When I go from 4 to 3, I go from the Gaussian fixed point to the sufficient fixed point for the Ising model. Now phi is not as sigma, phi square is like epsilon. They are not different operators. For the free theory, there is only one operator. One is the square of the other. For the strongly coupled, this is no longer the case. And these are the anomalous dimensions. Good. Okay, good. Now, here's the question though. How do we have these anomalous dimensions? Like, think of it like just the Lagrangian, from a Lagrangian point of view, right? I try to write down like some coefficient C times delta phi square, but I can always scale phi such that the coefficient of kinetic term is 1. I can always do that. That means it looks like phi is like mass dimension of phi is always d minus 2 over 2. I don't see how it can get like an irrational value, right? I should be able to always do that. And yeah, I can do that. So there is a difference between mass dimension and scalar dimension, which is actually why we can get these anomalous dimensions. And the way to see that is the way to resolve that, like if there needs to be a difference between mass dimension and scalar dimension, then there needs to be something dimensional, right? Like if OX, when I change X to L minus 1X goes like some power of it, some X to something, blah, blah, sorry, L to, actually, let me write here. It goes like L to mass dimension of O times OX, right? Now, this is fine, but if I want this O to be different than scalar dimension O, then I need another dimensional parameter. And the only resolution is that there has to be some microscopic length scale. Now, that's a very important point, because most of the time it is stated that at the critical point, there is no length scale. This statement is incorrect. You see this all the time, like in some just reviews or some books. They just say, oh, there is no length scale at the critical point, or there is no length scale for the conformal filter. Like, there is actually a length scale. There has to be a length scale. It's just that at the critical point, the behavior is independent of the microscopic details. We don't say there is no mass scale, but it is independent of the microscopic UV length scale. So the mathematical way to see this is as follows. So, okay, let's consider a function f(x), and let that be this A. A is a UV length scale. Okay, for a lattice theory, for example, this is the lattice space. Now, if I just say that at the critical point, this becomes fx, there is no dependence at A, this is incorrect. Okay, even at the critical point, I still need dependence on the UV length scale. However, it doesn't change anything, because the correct thing is that fx to the A becomes A times some power, I guess it was f minus delta f, fx. So at the critical point, it becomes like this. It is there for dimensional reasons. Now, if you look at the mass dimension of fxa, it is, I think this is like this is, let's see. I think it's like this. Now it becomes mass dimension minus it becomes, let's see, f minus delta f plus mass dimension of fx. And the mass dimension of x, as we say, defined as delta f. So it becomes mass dimension of f. Okay, I guess I should write this as fxs. Sorry, let me just write it a little better. Okay, it will be easy now. Sorry, fx comma a plus delta fx times fx. Okay, it will be like this. Now, if I consider the mass dimension of this fxa, then it becomes fxa minus delta fx plus mass dimension of fx, which we will take as delta fx. So, so this can be fxa. So this, in other words, this thing will be rational stuff. Like these guys will be rational, just d minus 2 over 2 or stuff like this. But these guys can be irrational. They can just real numbers, some arbitrary numbers. Because I have this form. And mathematically speaking, even though a over xi is very small, actually let me just a over x. So a is like the lattice spacing or UV length scale, and x is like the ordinate scale that we do the experiments. Let's say I am measuring the critical opalescence. X is a few centimeters, right? X is like few centimeters, A is like 10 nanometer or something like that. Even though this ratio is extremely small, I cannot set this to 0 because the function, the free energy or whatever it is of interest is not regular in these limits. Instead, so I cannot write fx 0. This is simply infinite. Instead, it becomes like a to some power, blah, 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 which is negative actually, times fx. So if I take a to 0, well, this blows up. So you cannot set it to 0, but it decouples from physics. So there's a microscopic scale there, but it doesn't affect anything. Now, this discussion is not that important, so if you couldn't follow it, it's fine. Okay, I'm just talking about this for completeness, and because there are some incorrect explanations, incorrect statements in literature. Like I put some references here, by the way, you can check them if you want. But the correct statement is that there is actually a UV scale, but it doesn't affect anything physical. So I can forget about it. It's only there for dimensional purposes. Okay, does anyone have any question? I think I wasn't very clear, but please check my notes. They're a lot better than what I'm trying to do right now. So they should be more helpful. But does anyone have any question? Okay. Okay, so long story short, we have these operators. We will be dealing with them starting tomorrow. These will be the irreducible representations of CFT algebra, these operators. And when you scale the parameter x, they behave like this. And this delta O is called the scaling dimension. And if you do little group formalism, like Bingham's famous little group formalism or stabilizer subalgebra of conformal group, which hopefully we can talk about tomorrow or maybe the day after tomorrow group, that would be SO 1,1 times SOD. And this SOD is rotations, standard rotation group, and this is the dilation group. And this delta, the scaling dimension, is actually the the representation label of SO1,1 dilation subgroup. So we label representations. This is what we do with the Poincare representations as well. Like it's called Wigner's little group formalism. And you can ask yourself, like, why do we say particles have spin? Why do we say particles have mass? Like, why do we choose these parameters? Because there's a mathematical reason for that. And that comes from Wigner's little group formalism. And more mathematically, the generalized version is called stabilizer subalgebra analysis. So if we consider conformal group and its stabilizer subalgebra, it will be SO1,1 times SOD in Euclidean signature, or SO1,1 times SOD minus 1,1 in Lorentzian signature. And this subalgebra, the labels of this representation is precisely this scaling dimension. So mathematical understanding of these objects would give us these scaling dimensions. Okay. And do I have time? I guess so, right? I guess, I have like 2 more minutes. Let's see. And one thing maybe I should say, these operators, you know, this any operator, like this delta, if they are free, they have something like, you know, for if scalar, it's d minus 2 over 2. If it's a vector, actually, what some examples, like if it's a gauge vector, it's d minus 2 over 2. If it's a fermion, it's d minus 1 over 2. Like you can find it from the kinetic term. This is the kinetic term, right? This needs to be d. So psi needs to be d minus 1 over 2, right? So at free theory, scale dimension, this delta O, delta O becomes same as mass dimension at free theory. And we get enormous dimensions when we move away from free theory. And when I say free theory, this also includes perturbation as well, because we do perturbations around free theory. So they are still free theory operators when you do perturbation theory. So for example, in the QED, if you're working with QED, you say mass dimension of like a gauge, the photon is d minus 2 over 2. Because even though it's coupled, it's weakly coupled, and we are doing perturbation expansion around the free theory and using free theory operators. Okay, so most of the stuff you do in standard models, actually this is the case. Oops, my bad. Anyway, so you can compute this stuff, and we said, okay, if this is like a strong coupling, if we are flowing to a very interactive theory, then they get enormous dimension, right? This is what we said. Now delta O becomes, let's say for a scalar, d minus 2 over 2 plus something. It's known as gamma O, right? It's enormous dimension. Now, we expect that almost all operators should get enormous dimension, unless they are protected by some identity, such as Ward identities. For instance, T mu stress tensor, it is D. It never gets enormous dimension. It's protected by the Ward identity. And actually, that is the reason why we expect conformal invariance if we have scale invariance. I will try to argue this tomorrow, or maybe the day after tomorrow, because to have scale invariance without conformal invariance in a quantum theory, like classically it's fine. You can have it classical, but in a quantum theory, to have scale invariance without conformal invariance, you need to have a protected vector operator. Otherwise, you cannot have it. Okay, so classically sure, but so that's why if you have a scale invariance in a quantum field theory, yeah, we say it's probably conformal as well. Yeah, I can also refer to some papers. I am 1 minute late anyway, so this should be a good place to stop. Yeah, we discussed all these nice things. And does anyone have any question? If not, I will stop recording.